Class 12th, subject physics, 6th chapter, superposition of waves. Superposition of waves. From this chapter, let us see vibrations produced in a string. Vibrations produced in a string. For that purpose, let us consider a string of length L which is stretched between two rigid fixed supports. So this will be the string of length L and which is stretched between these two rigid fixed supports. When this wire is plucked or if it is made to vibrate with any vibrator such as a tuning fork, then it will give rise to the stationary waves along the length of the string between these two rigid supports. So in this case, when that wire is plucked, when that string is plucked, at that time these waves will travel towards these fixed supports, that is end of this wire, and then from these rigid supports it will get reflected back, and hence there will be superposition between the incident wave and the reflected wave, and hence stationary waves will be produced. Hence there will be change of phase equal to pi by 2 radians, and in this way the string stretched between two rigid supports will vibrate with different frequencies, that is it will give rise to different modes of vibrations. So in order to explain these vibrations, let us consider some of the terms. Let L represents length of the vibrating string. L is the length of the vibrating string, that is the length of the string between these two rigid supports. Then due to plucking or vibrating that string, tension T will be created, and therefore T represents tension acting in the string. So T will be the tension acting in the string. Similarly, let M represents mass per unit length of the string. Mass per unit length of the string, that is also called as linear density of the string. And let lambda be the wavelength of the wave produced along the length of the string. So lambda is the wavelength of the wave. Now, as there are different modes of vibrations of that string, let us consider first three modes of vibrations of the stretched string. So one by one we will discuss these three modes. First mode. So in the first mode of vibration, if the string is plucked at its center, then it will give rise to only one loop in the form of a stationary wave. It will be consisting of two nodes and one antinode. So this will be the simplest mode of vibration of the stretched string, which will give rise to only one loop. If L represents length of the vibrating string, then length of the loop will be equal to lambda by 2, as there is formation of only one loop where lambda represents wavelength of this wave. Then the length of the loop will be given as L is equal to lambda by 2. L is equal to lambda by 2, and therefore from this lambda will be equal to 2L. Lambda is equal to 2L. Now if N represents the frequency of vibration of this first mode, that is the lowest frequency of vibration of the stretched string, if it is N, then we know the relation phi equal to N lambda. Phi equal to N lambda, therefore we can write N is equal to phi by lambda. N is equal to phi by lambda, and therefore N will be written as phi by 2L, as it is phi by lambda, but lambda is equal to 2L, therefore N is equal to phi by 2L. But in case of the vibrations or the waves produced along the length of the string, the velocity phi is given as phi is equal to square root of T by M. Phi is equal to square root of T by M, and therefore this N will be equal to phi by 2L, that is equal to 1 by 2L square root of T by M. 1 by 2L square root of T by M. This frequency is the lowest frequency of vibration of the stretched string, which is called as fundamental frequency or the first harmonic fundamental frequency or first harmonic. Now let us consider the second mode. So in the second mode, if the center of the string is again kept fixed, if that center of the string is now kept fixed with the help of any light object, and if the wire is plucked, if that string is plucked at a point midway between these 2 points, that is midway of any one of these segment, then two loops will be formed along the length of the vibrating string, and therefore there will be formation of 3 nodes and 2 antinodes. So in this case, 2 loops will be formed in the second mode, and therefore if L represents length of the string, then the total length will be equal to lambda 1, where lambda 1 will be the wavelength of this wave. Then from this we can find out the length of one loop. Length of one loop, that is equal to L by 2, because total length is L for 2 loops. Therefore for one loop it will be L by 2. So L by 2 will be equal to lambda 1 by 2. As there are 2 loops, it will be lambda 1 by 2, or we can write lambda 1 is equal to L, because these 2 will get cancelled. Lambda 1 will be equal to L. Now if N1 is the frequency of vibration for the second mode, if N1 is the frequency of vibration for that stretched string in the second mode, then N1 will be given as phi by lambda 1. Phi by lambda 1, that will be written as phi by L, because lambda 1 is equal to L. It will be written as, rearranging the terms, so multiply and divide it by 2, so 2 phi by 2L. 2 phi by 2L, and therefore N1 will be given as 2 into 1 by 2L square root of T by M. 2 into 1 by 2L square root of T by M, because this phi by 2L will represent the fundamental frequency, that is 1 by 2L square root of 2 by T by M, and therefore this N1 will be equal to twice of this fundamental frequency N. So N1 is equal to 2N. This higher frequency is called as second harmonic or first overtone. Second harmonic or first overtone. Then go for third mode. So in case of third mode now, at these 2 points along the length of the string, it will be kept fixed with the help of any light object, so that we will get in all 3 segments. Now if that wire is plucked at a point midway between any one segment, at this point or at this point or at this point, if it is plucked, then again it will give rise to stationary waves, and we will get 3 loops here. So between the 2 rigid supports we will get 3 loops, so that 4 nodes will be formed and 3 antinodes will be formed. So that if L is the length of the string between these 2 rigid supports, in terms of wavelength lambda 2 now for this wave, we will get L equal to 3 lambda 2 by 2, 3 lambda 2 by 2, and therefore length of one loop will be equal to L by 3. As there are 3 loops, therefore length of one loop, that is L by 3, will be equal to 3 lambda 2 by 2 divided by 3. As there are 3 loops, 3 will get cancelled, and we will get lambda 2 by 2. So L by 3 equal to lambda 2 by 2, or lambda 2 equal to 2L by 3. Lambda 2 equal to 2L by 3. If N2 represents the frequency of vibration for this third mode of that stretched string, if N2 is the frequency, then we can write N2 is equal to phi by lambda 2. N2 is equal to phi by lambda 2, that will be equal to 3 phi by 2L. 3 phi by 2L. It will be written as 3 into phi by 2L is 1 by 2L square root of T by M. 3 into 1 by 2L square root of T by M, but this factor is N, and therefore N2 will be equal to 3N. N2 is equal to 3N, and hence this frequency is called as third harmonic or second overtone. Third harmonic or second overtone. So in this way, in case of a stretched string, the produced vibrations will contain frequencies n, 2n, 3n, 4n, 5n and so on. Therefore, we can say that all harmonics are present in case of the vibrations of a stretched string. All harmonics are present in the vibrations of a stretched string. And now let us see the next point, that is laws of vibrating string. Laws of vibrating string. So in order to state these laws, we will have to consider the expression for the fundamental frequency of these vibrations of the stretched string, that is 1 by 2L square root of T by M, that is equal to N. And therefore the fundamental frequency of vibrations of stretched string is given as, so fundamental frequency n is equal to 1 by 2L square root of T by M. N is equal to 1 by 2L square root of T by M. In order to state these laws, as there are three quantities, length, tension and mass per unit length, and therefore in order to state these laws, one of the quantity will be kept variable and at the same time remaining two quantities will be kept constant. So when L is variable, T and M will be constant. When T is variable, L and M will be constant. When M is variable, L and T will be kept constant. And therefore from this, law of length, law of tension and law of linear density, that is mass per unit length, will be stated. So let us see these laws one by one. So first law is law of length. It is law of length. So in this case, L will be variable and T and M will be kept constant, and therefore this law will be stated as the fundamental frequency of vibrating string. The fundamental frequency of vibrating string is inversely proportional to vibrating length if tension in the string and mass per unit length of the string are constant. So this law will be stated as the fundamental frequency of vibrating string is inversely proportional to vibrating length of the string if tension T and mass per unit length M are constant. And therefore we can write n proportional to 1 by L, that is n is inversely proportional to L if T and M are constant. And therefore from this we can write NL equal to constant. NL equal to constant, or N1 L1 must be equal to N2 L2. Then let us consider second law, that is law of tension. It will be stated as the fundamental frequency of vibrating string is directly proportional to square root of tension in the string. The fundamental frequency of vibrating string is directly proportional to square root of tension in the string if the vibrating length L and the mass per unit length M are constant. So in this case, L and M are constant, and therefore mathematically it will be given as n proportional to root T if L and M are constant. So from this we can write n by root T equal to constant, n by root T equal to constant, or n1 by root T1 equal to n2 by root T2, n1 by root T1 equal to n2 by root T2. Then consider third law, that is law of linear density, that is mass per unit length of the string. It will be stated as the fundamental frequency of vibrating string is inversely proportional to mass per unit length of the string. The fundamental frequency of vibrating string is inversely proportional to square root of mass per unit length of the string if vibrating length L and tension T are constant. So the fundamental frequency of vibrating string is inversely proportional to square root of mass per unit length or linear density if vibrating length L and tension T are constant, and therefore we can write n proportional to 1 by root M if L and T are constant. From this we can write n into root M must be equal to constant, n into root M must be equal to constant, or n1 root m1 must be equal to n2 root m2. n1 root m1 equal to n2 root m2. Now from this third law, that is law of linear density, we can extend and we will achieve again two more laws. So for that, as linear density is nothing but mass per unit length of that string. Therefore, mass per unit length or linear density m equal to volume into density, that is mass, and it will be per unit length because that mass is volume into density. Therefore, it will be written as this volume will be area into length because that wire will be or that string will be in the form of a cylinder, and therefore its volume will be area of cross section into length. So area into length into density per unit length that will be written as area is pi r square, length will be L, density will be rho, and per unit length, that is upon L. So pi r square L rho upon L will get cancelled and we will get pi r square rho. So that will be the value of m, and therefore we know that according to law of linear density, n is proportional to 1 upon root m. N is proportional to 1 upon root m. Now this value of m will be replaced by pi r square rho. So n proportional to 1 upon root of pi r square rho. Now pi will be constant. If density is constant, then n will be inversely proportional to 1 by r. That is, n is proportional to 1 by r. And if r is constant, then n will be proportional to 1 upon root rho. And therefore we can write n proportional to 1 by r and n proportional to 1 by square root of rho. So from this we can say that the fundamental frequency of vibrating string is inversely proportional to radius of that vibrating string, and similarly we can state it as the fundamental frequency of vibrating string is inversely proportional to square root of density of the material of that string. The fundamental frequency of vibrating string is inversely proportional to square root of density of material of that string. So in this way, these two laws will be stated, that is n proportional to 1 by r and n proportional to 1 upon root rho. So these are the laws of vibrating string.